So far, robotic grippers have played an important role in industrial settings, contributing to factory automation and productivity enhancement. In such cases, grippers have been required to handle objects of certain specifications and move them according to predetermined sequences. However, due to advancements in technology, increased efficiency, and the advent of the COVID-19 pandemic and the era of remote interactions, the industries where robots are applied have expanded significantly, ranging from primary industries like agriculture to service industries that require human interaction. Compared to the past, this development has necessitated that robots, which previously only needed to handle predetermined objects, now possess versatility to operate in more diverse environments such as cafes and restaurants, handling a wider variety of items like fruits, dishes, and toys. However, existing grippers find it challenging to reliably meet these varying user conditions. So, we researched a surface pattern that could enhance the versatility of grippers. This pattern was inspired by studies on controlling friction using pillars and dimples. The goal is to ensure that the gripper could securely hold objects even if the surface was contaminated by fluids. This pattern features a geometric structure, where dimples are present within the pillars, allowing control over friction, and is therefore named DPPDF, dimpled pillar pattern for directional friction. Previously, there have been studies on dimples and pillars. Research on dimples has focused on controlling the directionality of friction by adjusting their shape and angle, while studies on pillars have aimed to enhance adhesion on fluid surfaces by mimicking the structure of a frog's foot. However, there are not many studies that simultaneously apply pillars and dimples to control friction. In this study, we combined variations in the shape of dimples and pillars with elastomeric materials. The pillars reduce the contact area, thereby increasing the contact pressure, which allows easier penetration through the fluid film on the object's surface. Depending on their shape, the dimples adjust the contact surface area and create a gradient of friction across different contact area. Overall, the geometric characteristics resulting from variations in the shapes of dimples and pillars, along with the deformation of DPPDF, maximize the directionality of friction. Here is a configuration to the design parameters that constitute the DPPDF pattern. The DPPDF has a total of 7 variables and features a structure where dimples are located within the pillars. The example in this page has hexagonal pillars with triangular dimples, but the shapes can change based on the first variable, dimple shape, and the second variable, pillar shape. Other design parameters that can affect the deformation and contact area of the DPPDF include the protrusion height of the pillars, pillar length, distance between pillars, dimple length, and the angle between the dimples and the surface. The design parameters can be represented in a table as follows. There is one 2-level parameter, dimple shape, while the remaining 6 parameters each have 3 levels. The dimple shape and pillar shape are discrete values, while the others are continuous values. User conditions include surfaces contaminated by fluids such as water and oil, considering both wet surfaces and typical, dry, surfaces. Here are example models to aid understanding. The geometric characteristics change according to the parameter values shown in each table. Notably, in Model 1, although the dimple shape is triangular, the dimple angle is 0 degrees, resulting in no dimples being formed, and the forward and backward directions are symmetrical. The sample of the DPPDF pattern is fabricated using SLA printing and F80 elastic resin for experimentation. This is a description of the test bench used for the experiments. A load cell was employed to measure the friction force. To ensure stable force and speed during the experiments, a 1/100th geared BLDC motor and a ball joint were used to measure friction reliably. A 1 kilogram weight was used to apply a consistent force on the sample pad, and both the sample pad and the weight were mounted on mounts fabricated using 3D printing. The experiment was conducted to determine the friction force of a pad made on an acrylic plate. Measurements were repeated 4 times in both the forward and reverse directions of the pad. The values measured in the forward direction were denoted as N forward, and those in the reverse direction as N reverse. The peak value of N reverse divided by N forward was termed the peak ratio, PR. This PR value was then used to calculate the S/N ratio for the wet and oily conditions. The experiments were conducted with water and oil at a depth of 2.5 millimeters. The experimental setup involved an orthogonal array with 1 2-level design parameter and 6 3-level design parameters. Experiments were conducted based on the combinations in the orthogonal array. The initial experiment comprised a total of 18 experimental runs. Using the Taguchi method's orthogonal array, the experiments were designed to find the optimal values, without the need to test every possible combination. Here are the 3D models for the first round of experiments. Each model, numbered from 1 to 18, corresponds to the design parameter combinations outlined in the orthogonal array, from experiment numbers 1 to 18. These are the result of experimental values from the first set of experiments, along with the corresponding signal-to-noise, S/N, ratios. The bigger the S/N ratio, the more suitable the values are for the desired objective. Based on the sensitivity graph of the S/N ratios for the first experiment, we can see that the optimal values are as follows. The dimple shape is triangular, the pillar shape is hexagonal, the pillar protrusion height is 3 mm, the pillar length is 6 mm, the distance between pillars is 2 mm, the dimple length is 4 mm, and the dimple angle is 43.6 degrees. This is the analysis based on the S/N ratios from the first experiment, presented through an ANOVA table. The ANOVA results indicate that the first parameter, dimple shape, which showed the lowest value in the sensitivity graph, and the fifth parameter, the distance between pillars, which showed the lowest slope, did not significantly affect the experimental results. For the second experiment, based on the results of the first experiment, we fixed the discrete parameters, dimple shape and pillar shape, and the parameter with minimal impact on the results, distance between pillars, to their optimal values determined from the first experiment. The remaining parameters, pillar length, pillar protrusion, dimple length, and dimple angle, were used for the second set of experiments. The dimple angle, which showed a consistent upward trend in the S/N sensitivity graph, was tested with the same level differences as in the first experiment. Meanwhile, the pillar length, pillar protrusion height, and dimple length, which did not show a significant slope in the graph, were tested with level differences set to half of those in the first experiment. Here are the result of experimental values and S/N ratios for the second experiment, along with the corresponding analysis of variance, ANOVA, table. This is the sensitivity graph analyzing the S/N ratio. The results of the second experiment indicate that the optimal values are a pillar protrusion of 3.5 mm, a pillar length of 6.5 mm, and a dimple length and angle of 4 mm and 43.6 degrees, respectively, as in the first experiment. Compared to the median value of -53 decibels in the sensitivity graph of the first experiment, the median value of -27 decibels in the second experiment indicates an improvement. The final derived pattern features a hexagonal pillar, triangular dimple, pillar protrusion of 3.5 mm, pillar length of 6.5 mm, distance between pillars of 2 mm, dimple length of 4 mm, and dimple angle of 43.6 degrees. This optimized result was compared with a symmetrical pad, where the dimple angle was 0 degrees, resulting in no dimples. The comparison showed directional friction asymmetry of 13.55%, 24.41%, and 22.54% for dry, wet, and oily surface conditions, respectively. When compared to the sixth experiment of the second trial, which had the worst experimental values, these optimized results showed improvements of 26.96%, 25.83%, and 26.19% for each respective surface condition. This is the final part of the video, showing the experimental footage of the optimized DPPDF and the ninth combination sample from the second experiment. The experiment demonstrates that in reverse consistently shows a higher value than in forward.